Alright, so far in this course, we've done a deep dive into energy and entropy balances. And we've used, thermodynamic properties like internal energy, enthalpy, and entropy to understand how things like temperature, pressure, or volume change throughout a process. And in the course of this course, there's been basically two sort of strategies we've taken to solve a problem. Right? And the first strategy, which was sort of general to any sort of chemical species, is we typically made an assumption that the fluid we were dealing with, if it was a gas, we typically assumed that we were dealing with an ideal gas. Or if we were dealing with a solid or a liquid, we assumed that we were dealing with something that was incompressible. And then by making those assumptions, that helped simplify our equations. And then we were able to just, solve some sort of differential equation that allowed us to get, internal energy, enthalpy, entropy, or things like work or heat. Right, so that's one sort of strategy that we've taken. Another type of problem that we've encountered involved us looking up thermodynamic properties from a table or a chart, so things like steam tables or the plots that we use to get values for refrigeration fluids, right? And so we use those tables and plots to get measured values of our thermodynamic properties, UHS. And then we plug those properties into our energy and entropy balances, and then solve for things like work or heat. All right. And so one of the challenging things about the beginning of this course is to kind of figure out, which of these strategies you're supposed to take when you read a given problem. And you've probably encountered the fact that if you try to apply strategy 1 on a type 2 problem or on a strategy 2 problem, that the strategy 1 doesn't really work. Okay? And the reason for that is because these type 2 problems are dealing with real substances. So type 2 problems are based on real substances. Okay? And real substances are not ideal. They're real. Okay? Right? And so in these real substances, or if you remember, when we derived the ideal gas equation, the two main assumptions that we made were that the molecules don't interact with one another, and the molecules also don't take up space so that they could overlap one another. Okay? For real substances, that's clearly not true. The molecules can interact with one another, and they have some sort of finite volume. All right? And so if we want to actually predict the behavior of real substances, we need to be using models that actually account for these different type of molecular phenomena, that account for interactions and account for the actual volume of molecules. So we need models that actually account for molecular phenomena. At the same time, we could spend all day thinking up, new sorts of models, but they won't matter unless these models actually, match and are able to predict the behavior of real substances. And so to do that, we need to validate the accuracy of our models against experimental data. And so, we test if these models are accurate by doing experiments and seeing if the values predicted by the experiments or predicted by the models match what we measure. And so we validate our models using data from measurable properties. So some measurable properties would be pressure, volume, temperature, etc. Okay? All right. And so what we're going to do here in Chapter 6, in order to connect our, sort of macroscopic observations to the molecular interactions that are going on in our substances, we need to be able to develop mathematical tools that will allow us to bridge those two things together. And so here in Chapter 6, we will learn about the mathematical tools for connecting molecular models to measurable properties.